Hello, and welcome to Astronomy 100. In this section, we're going to continue our discussion of remote measurements. It's important to remember that the objects that we want to learn about in astronomy are very, very far away. Distances we'll never be able to travel. And they're also in places that are very hostile to humans, so close-up measurements are just not available to astronomers in the traditional sense that they are for other sciences. But it's important to remember that our theme is that light coming from these objects is the carrier of information about these objects. And so if we can understand the nature of light itself, we can understand the objects that are producing the light. In this segment, we're going to concentrate our effort on understanding the nature of light. And what we're going to begin with is understanding some of the details about how light travels. And we know that light is energy, and we know that light is energy that goes from one place to another. And so the real questions that we need to begin with are, in what manner does light travel, go from one place to another? And so we're going to begin with describing the speed of light. In the early days of science, in the very beginnings of our Greek ancestors trying to understand the universe, they didn't fully understand the nature of light. And of course, they could still ask some simple questions about light. And one of the questions was, does light have a speed, or is light infinitely fast? You may notice in the world around you that it doesn't seem to take very much time or any noticeable time when light goes from one place to another. You don't notice that it takes time for the light in your home when you flip the switch to fill the room that you're in. It seems as if light just instantaneously fills the room. When you flip on your car headlights, you don't notice the beam of light going off into the distance. It seems like it's instantly off at the distance it needs to be. So you can understand how it seems to be confusing as to whether or not light travels infinitely fast or if light has a speed. The first scientist to try to answer this question was a Danish scientist by the name of Ole Romer. And in 1676, Romer understood that light, if it has a speed, its speed would be incredibly fast. And so what he determined was that it was needed to measure light over a very big distance to be able to measure the speed of light if it had a speed. And so earlier in the 17th century, Galileo had already discovered that Jupiter had 4 moons that revolve around it. And so this knowledge was something that had been around for a very long time. Romer understood that if you have the ability to go outside with a telescope and observe the moons of Jupiter, over a period of time, you could observe the movement of these moons as they orbit around Jupiter. And let me demonstrate this for you in a video here. This video was a series of images that were taken in the year 2002 by an observer, an astronomer in England. And what he did was he went outside and took picture after picture after picture of Jupiter and 3 of its moons. So here is Jupiter. It's purposely overexposed to have the ability to see the fainter moons more readily. But you can actually see the moons, Io, Europa, and Ganymede, slowly move as time goes by. And notice that the minutes are going by quite rapidly, so this has been sped up quite a bit compared to what you would normally see. But what I want you to notice is the moon Io will appear to move behind Jupiter. And this was the reason why he was taking these pictures. He wanted the ability to capture on video the movement of the moon Io as it passes behind Jupiter. He's able to do this because there's a specific calculation you can make that will tell us precisely when Io will do this, so he knew to be outside to take these pictures at the appropriate time. So this is something that is quite easy to see. And the reason why this is possible is because the moons of Jupiter are moving quite regularly, sort of like clockwork. And so there's a predicted time that you can go outside and witness any one of these moons passing behind Jupiter. Well, here's what Romer noticed. Romer noticed that when the Earth and Jupiter were about as close as they could possibly be, the Earth in its orbit and Jupiter in its orbit, what he noticed is that when you went outside to witness the event of any one of Jupiter's moons passing behind Jupiter, it would end up that the moon would pass behind Jupiter a few minutes ahead of schedule, as if it's happening prematurely compared to when you're expecting it to. However, when the Earth and Jupiter were about as far apart as they could possibly be, witnessing the same event meant that the moons of Jupiter would actually occur, the passage of the moons behind Jupiter would occur a few minutes later than expected. So in other words, it would happen late when the distance was the largest, and it would happen early when the distance was the shortest. Roemer's conclusion was that this is because light has a speed, and it must have a speed to have a difference between the distance being short versus long, and it being something ahead of schedule or behind schedule based on the distance. Because speed is the distance something travels over a period of time. So Roemer was able to deduce that light has an actual speed, and then he took it one step further, and he was able to calculate the speed of light. So in 1676, we had the first attempt at determining the speed of light. And the number that Roemer comes up with is actually not correct, although it is fairly close to the accepted value today. Now, why was his number incorrect? Well, in 1676, the ability to measure time very accurately was just not something that was available at that time. And the knowledge of the distance between the Earth and Jupiter was known to a rough degree, a certain amount, but it was not exactly as precise as we know today. So a small error in the distance and a small error in the timing produced an error in the speed of light. But what it demonstrated is that light has a speed, and that speed is something that we can actually calculate and determine. Now today, when we determine the speed of light, we determine it by doing an experiment in a laboratory. And when this experiment is conducted, the experiment is always done in an environment called a vacuum. And a vacuum is when you have a chamber or an environment where all of the air has been taken away. And the reason why astronomers want to have the speed of light measured in a vacuum is because there is a need to be able to measure the speed without it interacting with anything along its path. When light goes from a source to its target, if it has to interact with any air in the process of traversing that distance, then of course that effectively slows down the speed of light. To know what the speed of light is in its complete ability to travel from one place to another without being impeded in any form, you need to do it in a vacuum. So take away all the air in between its source and the target, and you can determine the speed quite accurately. When we do this, something rather interesting happens. What we end up calculating is the speed of light to a very high degree of precision. But when this experiment is repeated in laboratories all around the world under various different conditions, different equipment, different people doing it, what we end up with is one number that is always the same number. And that number is 186,282 miles per second. We actually know the speed of light to about 9 decimal places following that, but we're going to round it to the nearest mile per second. So the speed of light is a constant value of 186,282 miles per second. Now, to give you a feel for just how fast the speed of light is, if you remember in a previous section of the course, we talked about orbital velocity. And in that segment, we talked about the minimum speed needed to orbit around the Earth. And orbital velocity for the Earth is 17,500 miles per hour. And if you were to orbit the Earth at 17,500 miles per hour, it takes about 90 minutes to make one orbit around the Earth. If you could travel at the speed of light, you would actually circle the Earth 7.5 times in 1 second. So 90 minutes to make one orbit at the speed that our modern spacecraft orbit the Earth, or 7.5 times around the Earth in 1 second. And what you can see is there's a tremendous difference between the speed of our modern spacecraft and the speed of light. So 186,282 miles per second. To give you some other numbers to help you understand just how fast this is, the speed of light is a number that gives us a distance and a velocity that would allow you to travel 11 million miles in 1 minute. So in 1 minute of traveling at the speed of light, you will go 11 million miles. If you like miles per hour better, as most people do, this is 671 million miles per hour. So in 1 hour, you could travel 2/3 of a billion miles. And if you were to travel at the speed of light for a year, you will travel a distance of almost 6 trillion miles. So the speed of light is extraordinarily fast, but it is not infinitely fast. Now there's some other interesting things about the speed of light that need to be, of course, introduced at this point. So let me go through them with you. First of all, it's important to understand that light speed is the fastest speed that the universe allows. So there is no traveling faster than the speed of light, as you will sometimes mistakenly hear in movies produced in Hollywood. There is no traveling faster than the speed of light. The speed of light is the fastest speed allowed in the universe. And material objects cannot travel at the speed of light. Anything made out of atoms is forbidden from traveling at the speed of light. You could travel very, very close to the speed of light. You could travel at 99% the speed of light, but the ability to go at 100% the speed of light is forbidden by the physics of our universe. So what that means is there will never be spacecraft that you could accelerate up to and become actually at light speed. You could get close to it, but not actually at it. So that's another mistake that Hollywood will also make. And then lastly, the speed of light, because it is a speed, that means that it will take time to travel various distances, meaning that the light coming from an object takes a certain amount of time before it reaches your eyes. And let me show you a few examples of this. For instance, when you're outside looking at the moon, as you see in this beautiful picture on the screen, you were looking at the moon at a distance of about 234,000 miles. That's the distance between the moon and the Earth on average. But the light that leaves the surface of the moon and then travels to your eyes, allowing you to see it, took about 1¼ seconds to get to you. So you are forever looking at the moon the way that it looked 1¼ seconds ago. Now, if we switch to something like the sun, which is even further away, the average distance between the Earth and the sun is 93 million miles. Traveling at the speed of light, traveling the distance between the sun's surface, where the light is emitted, comes off of the sun and reaches your eyes here on Earth, traveling 93 million miles takes 8 minutes and 19 seconds. So what that means is when you look at the sun in the sky, you are actually seeing it the way that it looked more than 8 minutes ago. It just takes that long for the light to travel to you. If we switch to objects that are even further away, such as Saturn, the distance between the Earth and Saturn on average is about 800 million miles. So if you were to go outside on a night and look at Saturn, perhaps through a telescope, the light has traveled 800 million miles to reach you. But the light traveling that enormous distance takes 1 hour and 12 minutes to eventually reach you. So there is no way possible to see Saturn the way that it looks right now. We are forever seeing Saturn the way that it looked a little more than an hour ago. Now these distances are close. If we switch to the distances between us and the stars, it becomes even more incredible. Let's look at a few examples here. This photograph here is the Orion Nebula, with the constellation of Orion surrounding it. So the Orion Nebula is, there's my pointer. So there's the Orion Nebula, and then of course the constellation of Orion that surrounds it there. So let's look at some of the distances involved for these objects here. For instance, this star here called Betelgeuse, when you see it, the light has left Betelgeuse and has traveled for 427 years to reach you. So you are seeing Betelgeuse the way that it looked 427 years ago. This star here called Rigel is at a distance that it requires the light 773 years to travel from that star to your eyes. The Orion Nebula here is even further away. When you look at the light coming from this cloudy part of our galaxy, that light has traveled for 1,600 years to reach you from that tremendous distance. And taking it one final step even further, if we were to look at a particular galaxy, such as this one here, the galaxy known as M51, the light that you see from this galaxy has taken 23 million years to reach you. So because light actually has a speed, it will always take time to travel enormous distances, and it always means that you were looking at something the way that it looked in the past. In the next segment, we're going to talk about the consequences of this and the other features that light has. I hope you'll join me.